Hello guys, welcome back to my channel Gamma Digamma. So in this video I would like to do one of those not so hard integration questions and let's get started. Okay, so assume we have this integral from 0 to infinity e to the negative n x squared cosine of ax squared dx. And let's call this I1. Now to solve this, I tried the Leibniz rule of differentiating under the integral sign, but it wasn't particularly any helpful. At least for me, it sort of complicated this integral even more by introducing an extra algebraic factor of x squared. So what I did was I just decided to go a fairly conventional and simple or obvious route. Integral from 0 to infinity e to the negative nx squared, and then I generalized the cosine as e to the I ax squared dx. I call this I, and this will be useful for us because e to the I theta, if you remember, is cosine theta plus I sine theta. This is the Euler's identity, and when I do that I can basically club some terms in the exponential part. E to the, I can pull in an x squared, maybe negative x squared actually, n minus ia dx. Well, n is a constant, a is a constant, I is the imaginary part, so this entire thing n minus I is just another number. It's a complex number, but it's still a number. So we can use the properties of the general Gaussian integral and write the final answer for this. It's going to be half square root pi divided by square root of n minus ia. Okay, are we done? Is that all? Is this a video like a waste of your time? Well, I can do one thing, because I don't like to be on the bottom. I like to be on the top. So I'm just gonna basically sort of try to rationalize this by multiplying and dividing by the square root of the complex conjugate of this guy. So I'll have square root of n plus ia divided by n plus ia. Eventually both of them cancel out to 1, so it shouldn't be a problem. Half square root of pi square root of n plus ia over square root of, well, n squared plus a squared okay, you can call that I. And some of you may think, now we're done, right? Everything looks nice, but it doesn't. I'm not satisfied, because I say we can convert this square root of a complex number into another complex number, and that's only possible because we're working on the complex plane now. It wouldn't have been necessarily possible to convert the square root of a real number into another real number, like apart from itself. So that's like a weird thing with the complex plane, but it's really powerful, and that prevents us from being lazy, and it tells us we need to do more than this. So what I'm gonna do is, on the next page I'm gonna take this part, the top part. We can't do anything with the bottom part because it's already real. It's n squared plus a squared is already real. I'm gonna take this top square root part on the next page, and try to get this into a better form. And if you don't know how to do that, well, today is your lucky day. So see you on the next page. Okay, our motivation for existing on this page at least is finding the square root of this number. So, well, this number is a complex number, so it belongs to the complex plane C. And since it belongs to the complex plane, we can express this, if you call this Z, as x plus iy, where x and y are real numbers. So any complex number can be expressed as this form, where the real component and the imaginary component at least are two distinct real numbers. I mean, they don't need to be distinct too, but whatever. Okay, since we can do that, so we have square root of n plus ia is a complex number, therefore it can be expressed as x plus iy. Now I would like to take the square on both sides, because doing that helps me eliminate this surd over here. So I just have n plus ia is equal to, well, x squared minus y squared plus I times 2xy. I just grouped the I and non-I terms together. And note that I squared is -1. That's why we got negative y squared and not positive y squared. Now equating the real and imaginary parts, so n is x squared minus y squared, 2xy equals a. Well, x is a over 2y, and now we can substitute this in this formula. So n is equal to a squared over 4y squared minus y squared, and we're going to end up with a quartic, 4y to the 4th plus 4ny squared minus a squared is equal to 0. And luckily we don't have any cube terms, so we can use the quadratic formula, but instead of having just a y, we have y squared, because it's a quadratic in y squared. So y squared is equal to minus 4n plus and minus square root of 16n squared plus 16a squared divided by 8. I'm just using the quadratic formula that you learned in high school. So minus 4n plus or minus 4 n squared plus a squared over 8, and it looks like we can cancel a factor of 2 from everywhere. So y squared is negative n plus or minus square root of n squared plus a squared over 2. Now notice that when we take a square root here for y, we have minus n plus or minus square root of n squared plus a squared over 2. But since we're taking a square root, we need to consider both the positive and the negative branch, so plus and minus outside. Now notice we can make a decision about the plus and minus inside, because if this is a minus in, you'll have negative n, negative square root of n squared plus a squared. So two negative terms added together will give you another negative term. And since we want y to be real, according to this condition, we can't have negative terms inside the surd or the square root, which means we only take the positive, we ignore the negative. So y ultimately becomes plus or minus. We can't ignore the exterior plus and minus, because it doesn't matter what we have outside. I mean, even negative integers are real numbers, so that doesn't matter. But having a negative inside the square root matters, because I is square root of -1. And then it automatically becomes complex if we have negative stuff inside square roots. So minus n plus square root of n squared plus a squared. We ignored the negative over 2. So that's y. Now what is x? We know y. We know what's x. Well, x is a over 2y. Okay, so for that, let's just write plus and minus as it is. A over 2, just taking the reciprocal of this, 2 over negative n plus square root of n squared plus a squared. Fine. Now I would like to sort of rationalize the denominator in this case. So n squared plus a squared, but instead of minus n plus n over square root of n squared plus a squared plus n. And this is useful because we can use the difference of squares identity on the denominator here and convert it into something that's a little more acceptable. So 2 over, well, first term squared is n squared plus a squared. You just lose the third. Minus n squared times square root of this top guy, square root of n squared plus a squared plus n. So n squares cancel out. A squared under square root is just a, that cancels out with this. 2 and a square root of 2 will give you a square root of 2 in the denominator. So we can take a common square root for everything. We have finally square root of n squared plus a squared plus n over 2. And I'm not ignoring the plus and minus. So this plus and minus is because of y, and because x is equal to a over 2y, there is no negative, otherwise we would have flipped the order of plus and minus. It would become minus plus. So be careful with this notation. So x is this, y is that. Okay, so I'm gonna do one thing. I'm gonna call the positive branch of x plus, which is just this positive part of it, and the negative branch x minus. I'm going to do the same with y. I'm going to call it y plus and y minus. So our solutions for this quartic that was there, well, the solution for the entire thing, 4 solutions, x plus y plus, for example, and the other one is x plus y minus, x minus y plus, and finally x minus y minus. Now we need to make a choice for one. Notice our integral was going from 0 to infinity. X was going from 0 to infinity, which means that x is positive or even equal to 0. So we need to choose a positive branch for x. So therefore x is just going to be square root and n squared plus a squared plus n over 2. And then notice this original equation, a was 2 times x times y, and a is positive, n is positive. We defined that by convention. So if x is positive, y has to be positive in order for a to be positive. So y is like the positive branch of negative n plus square root of n squared plus a squared over 2. So basically the square root of n plus ia is just square root n squared plus a squared plus n over 2 plus I times square root of negative n plus square root of n squared plus a squared over 2, at least for the conditions that we had defined, and n and a are greater than 0. So fine, we're going to use this and plug it back in the integral. Let's do that. So our I is precisely going to be half square root of pi over square root of n squared plus a squared, along with this square root of n plus ia term. That's a lot of square roots. So we have half square root of pi over square root of n squared plus a squared, and then this other term is going to be square root of n squared plus a squared plus 1 plus n over 2 plus I times square root of n squared plus a squared minus n over 2, and we could do some simplification. So so we have half square root of pi over 2 and well, we can take a big square root of n squared plus a squared plus n square root of n squared plus a squared plus, well, the imaginary part, which is square root of n squared plus a squared minus n over n squared plus a squared. There was no need for a surd over here actually. And well, what's I? I is integral from 0 to infinity e to the negative x squared e to the it's n x squared e to the iax dx, which you can split as e to the negative nx squared cosine of ax dx plus I times integral from 0 to infinity e to the negative nx squared sine of ax dx, under the condition that a and n are both non-negative rather. They could be 0 though. And then just compare. So like this guy is simply equal to half square root pi over 2 square root of n squared plus a squared plus n over n squared plus a squared, and then this is simply equal to half square root of pi over 2 square root of n squared plus a squared minus n over n squared plus a squared. And there, I hope you enjoyed this video. We essentially started with one integral, defeated two in the process, given some conditions. So I hope you enjoyed this video and learned something if you didn't know this method already. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math, and peace out.